Hi, my name is Shayan. I'm a senior electrical engineering major at UCLA.
Hi, I'm Patrick. I'm also a senior electrical engineering major at UCLA, and we'll be presenting to you our Capstone project for the class E180DADB, which is called Gait classification. Gait classification has applications in the world of healthcare, rehabilitation, and sports performance analysis. Our specific classification has three types of movements to classify, which is short strides, long strides, and sitting. And now on to the implementation of our project.
Okay, we have Patrick on the laptop doing the data acquisition, and I'll have the sensor tiles on doing the walking. So we're doing the short strides.
Set, go. Okay, stop. That's 10 seconds.
We're performing the data acquisition for long strides currently. So I'll go when Patrick says go.
Okay, ready, set, go. Okay, that's it. So this is Shayan, and he's going to be doing the sitting test. So Shayan is going to be operating on the laptop and sitting at the same time. And he will be sitting down for 10 seconds, and the Beagle will collect the data from there. So whenever you're ready.
Okay, can do this.
Notice that the sensor is not blinking, so it's collecting data. And the data is finished now.
In this section, I want to demonstrate the files that was gathered via the dual sensor data acquisition version 1.1. The final data that we used were 15 trials for each of the three motion types. That means 15 trials of data for short strides, 15 trials of data for long strides, and 15 trials of data acquisition for sitting. And that includes sets of data for each of sensor 1 and sensor 2. As an example, I will open up the files and demonstrate a couple of them. Now this is the motion data output for sensor 1 short strides trial number 11. This is the data for motion data output sensor 1 long stride trial number 11. And this is the motion data output for sensor 1 sitting trial number 11. Motion data output for sensor 2 short trial number 11. Motion data output for sensor 2 long strides trial number 11. And this is motion data output for sensor 2 sitting motion trial number 11. In the beginning, the motion data output files produced by the dual sensor data acquisition version 1.1 did not include timestamps. So the C files acquire low-pass continuous 1.c, where were edited to include a timestamp in the motion data output files. Here I will demonstrate that edit. We introduced the data structure for the sample time and for the file to print the timestamp to both of them. Please note that the edit on the acquire low-pass continuous file was also done for the continuous 2.c because we're gathering data from two sensors, so the sensor 2 also needs to have timestamps on its motion data output files to be printed. So here's a quick demonstration of the edit on the second C file. And here is to be printed, the sample time to be printed in the motion data output file. Was done. Now, the motion data output files, they have to be moved to the motion data directory. And here are the files: motion data output sensor 1, long strides 1 through 25, short strides 1 through 25, and sitting motion 1 through 25, and that includes for sensor 1 and sensor 2. Now, because we used to have more motion data output files, the other ones that you may see here is from the previous trials. Now, in order to perform the feature extraction correlation, a list has to be made from the motion data output files, and this lists the motion data output files in order with the specific motions. By example, I will concatenate one of them to demonstrate. Now, this is the Xcore file list for the short stride sensor 1. This is the concatenated Xcore file list for the long stride sensor 1. This is the sitting file list for sensor 1. This is the short stride file list for sensor 2. Long stride file list for sensor 2. And finally, sitting file list for sensor 2. Now, the use of the feature extraction correlation for us was to get the autocorrelation of the features. Now, first was that the feature produced is cross-correlation of the features and autocorrelation of the features, and you choose how to do it. That means that you choose which axles of the motion you want to perform cross-correlation and autocorrelation on it. In order to do that, the C file has to be edited. Now, I will demonstrate the edits on the C file. Now, this is the waveform Xcore correlation file that was edited by Patrick and I in order to choose which axles of the motion data output files we would like to perform cross-correlation and autocorrelation operations on it. Now, we added the temporary data structures here in order so we can move around them conveniently. Now, this is the line that scans the lines of the motion data output files and reads them into the data structures created before, and therefore after that performs the autocorrelation and cross correlation on it. Now this is a time vector, and here by moving the amplitude vector 2x and amplitude vector 2y, you can choose which columns of the motions for the motion data output files you would like to perform the cross correlation on it. Now, motion data output file includes the following columns: sample time, axle X, axle Y, axle Z, gyro X, gyro Y, gyro Z, and magneto X, magneto Y, and magneto Z. And that is for 2 sensors. Now, by moving the amplitude vector 2x and amplitude vector 2y in the correct position, you can choose which column of the motions for the motion data output file you would like to perform the cross correlation and autocorrelation operations on. And this is done in 2 sections because the waveform X-core feature does that for a pair of motion data output files, which one corresponds to sensor 1 and the other corresponds to sensor 2, and you can choose that based on the input. .sh and provided input the file list, the X-core file list that in the previous parts of the video I showed what they're for. It will compute features for you and graphically display them in a histogram form. Also provide output CSV files that will numerically represent the histograms, and also provides you with a integrated X-core summary. I will start the computation. Now here there are 45 input files which correspond to 15 trials for 3 types of motion, and that would be 45 files in total. The system will compute its own features, display them in a histogram form, and also output a CSV file that numerically represents the histogram. Also provides you with a integrated X-core summary CSV output that will show the cross correlation of the axis of the motion that you chose from those input files, and it will does that for a pair of files going from your here is the short stride motion. It will perform the operation for all the 15 short stride motions versus all of the files. So the indices form will start from 0, 1, 0, 0 going up to 0, 14, 1, 0 going up to 1, 14, similarly going on to 14, 0 up to 14, 44. Here is the graphical representation of the extracted features. And here is the numerical representation of the features computed by the system. Now, we did not specifically get our features from this output file because to our senses the autocorrelation was more distinct. Now the integrated X-core summary, it outputs the cross correlations and autocorrelations for the files that you include in your X-core file list. I will demonstrate the examples here. Now we performed the feature extraction for all of our lists for two important axles of motion, and one of them was to perform features for axle Y versus axle Z, and that means for the acceleration Y and acceleration Z columns. And the other one was to perform the feature extraction for axle Z versus acceleration Z versus gyrometer Z. Now this shows the integrated cross-correlation summary for sensor 1 for the short type of motion, and this corresponds to acceleration Y versus acceleration Z. Now the 1xx here, it corresponds to autocorrelation of the first axis that you chose in your first file. Autocorrelation, and 1yy column corresponds to autocorrelation of the second axis in your first file. And similarly, it does that for the second file, and cross correlation of the two columns in the first and the second file. One of the features used in our motion classification was the autocorrelation of acceleration Y for each of the types of the motion. Now the important files that were involved in gathering that feature are the integrated X-course summary for the short, and I will concatenate them here to demonstrate as an example. Now, this is the integrated X-course summary for sensor 1 short. Integrated X-course summary for sensor 1 long. Integrated X-course summary for sensor 1 sitting. And similarly, same short, long, and sitting files for sensor 2. Now, as an example, I will demonstrate which parts of the data in this are important to us. Now, this is the integrated X-course summary for short stride for sensor 2. Now, I mentioned that our feature was the autocorrelation of acceleration Y, and I will show that which one of the rows is corresponds to that, which columns and which rows. Now, 1xx, as mentioned before, corresponds to autocorrelation of the first column that you chose in the C file in the first file. Now we want the autocorrelation of acceleration Y of each file, so we will grab the 1xx column for the rows that correspond to both same indices. So that means that we grab the 1xx for 0, 0, 1, 1, 2, 2, 3, 3, similarly going to 14, 14. In order to find features, we had to review the motion data outputs manually, and that meant observing them and trying to find patterns. Now, in part of our process, we performed different algorithms on the motion data output files, and one of them was to find the mean of each column for each trial. So here is the collected means for each trials of files, and that corresponds to the short stride files 1 through 25. This is the mean corresponding to each column: acceleration x, y, z, gyrometer X, Y, and Z. We do not include magnetometer data, and the reason is because the magnetic field of the Earth does influence the magnetometer sensor when you walk in different directions. Now this is the collected averages for the Sensor 2 set of trials. This file represents the integrated X-score summary files which were collected for the autocorrelation of the file indices 00, 11, 22, going all the way to 1414. And those rows were collected for each of the three types of motion, being short, long, and sitting. And here the white columns correspond to short, yellow columns correspond to long, and green columns correspond to sitting. And 1xx is the autocorrelation of the first file, 1yy is the autocorrelation of the second column for the first file, and similarly you can follow the nomenclature. Now this data here was observed in order to find a pattern that can be used for classification. Now we observed the autocorrelation and cross-correlation for axes of motion of acceleration y and acceleration z. And after the observation, it was found that the autocorrelation for acceleration y is distinct. And that was one of the features extracted. There are 4 features for motion classification, and the other 3 are as follows. In sensor 1, in the data collected from sensor 1, we extracted 2 features. The first one was the autocorrelation of acceleration y, and the second one was the mean of axle y data. In sensor 2, there were 2 features extracted, and that was the mean of acceleration z and the mean of the gyrometer z data. Now we have extracted 4 features from our raw motion data output files. The features are as follows. From sensor 1, autocorrelation of the acceleration y, mean of the acceleration y. From sensor 2, mean of gyrometer z data, and mean of acceleration z. These are the raw form of the features. And after iterations with the neural network, it was found that the performance enhances by mapping the number within a fixed range. So it was decided to map the numbers to -π/2 and between -π/2 and π/2 using an arctangent function. So here we have the arctangent of our original features, and that corresponds to the final form of the features. Now we're moving on to the machine learning algorithm and display how the neural network works here. Now, so far we have collected 4 features, and those are autocorrelation of acceleration y from sensor 1, mean of axle y data from sensor 1, mean of acceleration z data from sensor 2, and mean of gyrometer z data from sensor 2. And those numbers were mapped to the range of -π/2 to π/2 using an arctangent function, and thus currently created a training dataset and testing dataset. I will display the training dataset and testing dataset and perform training and testing for the system using the fan library. Now, XOR the data, this shows the training dataset file, and here we have 30 sets of data, and that is 10 rows for each 3 of types of motion. And we have 4 inputs, which is our 4 features, and 1 output, which is the motion type. -1 corresponds to the motion type of short strides, 0 corresponds to motion type of long strides, and 1 corresponds to motion type of sitting. Now the system is doing the training, and the training is complete, and here you can see the results, and all the errors are below 0.1, and that is really successful training. Now this is the test data file. For testing, we used 5 trials for each of the motion types, which are different from the training trials. Now we have 5 trials to test for the -1, which was the short stride motion, and 5 trials of data to test for type 0, which is long stride motion, and 5 trials of data to test for sitting motion. Now the system has performed the testing, and the testing is very successful. As you can see here, all of the errors are below 0.1. Now the testing and the training of the system, after the testing and training of the system, we drew up confusion matrices for both of the training and the testing. And because the training and the testing were completely successful in each trial, that resulted in perfect confusion matrices. Now this is the confusion matrix for the training. We had 10 trials of training for each type of motion, and here, as you can see, we have a perfect confusion matrix for training of the system. Also, as testing of the system was completely successful in each trial, this is the confusion matrix for the testing, and here we have a perfect confusion matrix. We tested 5 trials of motion for each type of motion, and as you can see here, both of the confusion matrices, they don't have any off-diagonal non-zero elements, as they're perfect, as the training in the system was successful in every single case. To sum up here, we gathered 15 trials of data for 3 types of motion: short stride motion, long stride motion, and sitting motion. Used 10 trials of each 3 types to train a neural network using the fan library, and 5 trials of each 3 type to test the system. Now, the system was trained successfully on those 10 trials of motion and performed positively in every single case, arriving at a perfect confusion matrix for the training. And the testing of the system was also successful in every single case, arriving at a perfect confusion matrix. Finally, we were successful in training a system using neural network on the data that was gathered by two sensors for the motion types of short strides and long strides and sitting, and the system is able to classify successfully between these three motion types. Thank you for watching.